Hello, good morning to all of you. So in today's class, we're going to discuss the 8085 programming model. Now, 8085 programming model, as we've already discussed, it includes 6 registers, one accumulator and one flag register as shown in the figure. Now, in addition to that, it has a stack pointer and the program counter. Now, as represented in the diagram, there are 6 general purpose registers, B, C, D, E, H, and L. These are 8-bit in size. It has an accumulator which is also of 8-bit in size. It has stack pointer of 16-bit and it has a program counter of 16-bit. Now what we have is we have a bidirectional data channel or data bus which is of 8-bit in size and a unidirectional address bus which is of 16-bit in size associated with the various registers. Now let us move on to registers. As I've already discussed in the previous class as well, there are 8085 has 6 general purpose registers, namely B, C, D, E, and HL. These registers are used in order to store 8-bit data, but these registers can be paired up in order to handle 16-bit data, and the pair description is as B, C, D, E, and HL pair. Now the programmer can use these registers to hold data or to perform any whole data whenever the microprocessor is performing any operation. Likewise, accumulator. Now, accumulator is a 8-bit register that's a part of arithmetic logical unit, and it's used during arithmetic logical operation. To add to it, accumulator forms a default operand in almost all the operation that the microprocessor performs. Now, the result of the operation that the microprocessor performs is also stored in the accumulator, and the accumulator is identified by a character A. Now let us move on to the flag register. Now the flag register has 5 flip-flops realizing 5 different flags which are set or reset based on the data condition of the result. We have zero flag, we have carry flag, we have sign, we have parity, and we have auxiliary carry. So these are capable of representing the status of the data condition. Now, the organization of the flag register is as follow. In the flag register, D0 represents carry flag, D1, D2 represents parity, D4 represents auxiliary carry, D6 represents 0, and D7 represents sign. Again, I'll repeat it. D0 represents carry, D2 represents parity, D4 represents auxiliary carry, D6 represents 0, and D7 represents sign flag. Now, the various flags they play a very critical role in decision making process of the microprocessor. As I've already added to it, that microprocessor most of the instructions that are defined for 8085 microprocessor makes use of these carry flags in order to make certain decisions. Now, program counter, as we have already discussed, program counter is a 16-bit memory register that is responsible for sequencing the execution of the various instruction. The microprocessor uses the register to sequence the execution of the instruction. The function of the program counter is to point to the memory address from where the next byte is to be fetched. So once the next byte, once the byte is being fetched, the program counter is incremented to point to the next byte. So a program counter is a memory register that is responsible for sequencing the execution of instruction. So it points to the byte that is to be fetched next. So once the byte is fetched, the program counter is incremented to point to the next byte. Now, likewise, stack pointer, as we've already discussed, is a 16-bit memory register that is capable of pointing to the read-write memory called as stack. Now, stack is generally used whenever a program has a subroutine or a multiple subroutine in it. So it's used in order to store the address, return address whenever the subroutine is being called. So the address is pushed into the stack, and likewise, whenever you want to return back to the calling function, the address is popped from the stack, and the control transfer takes place. So that is the utility of the stack pointer. Now let us move on to the important aspect, that is 8085 addressing mode. Now each instruction performs an operation on particular data called as an operand. So we already know that instruction is capable of performing operation on a data that's called as an operand. And operand should be specified for an instruction to be executed, definitely. So whenever an instruction is to be executed, the operand has to be specified. And then the operand may be in the general purpose register, or it may be in the accumulator, or it may be in the memory location. Now these are the three holdings where data may be present. The data may be present in the general purpose registers, or it may be present in the accumulator, or it may be present in the memory location. Now, the way in which the operand is specified in an instruction is called as addressing mode. So this is very much important. The way in which the operand is specified in the instruction is called as addressing mode. So each instruction is capable of performing operation on the operand, and the operand has to be specified in the instruction whenever it's to be executed. Now the operand may reside in the general purpose register, or it may reside in the accumulator, it may reside in the memory location. Now the way how the operand is specified in the instruction is called as addressing mode. So this is a very important concept that you need to understand. The way how we specify the operand in the instruction is called as the addressing mode. Now the various addressing mode in 8085 microprocessor are immediate addressing mode, register addressing mode, direct addressing mode, register indirect addressing mode, and implicit addressing mode, right? So again, I'll repeat it. The various addressing mode in 8085 microprocessor that we have are immediate addressing mode, register addressing mode, direct addressing mode, register indirect addressing mode, and implicit addressing mode, right? Let us start with the description of the various modes. Now, immediate addressing mode. Now, in the immediate addressing mode, the operand are specified in the instruction itself. Again, I'll repeat it. In immediate addressing mode, the operands are specified in the instruction itself, right? So what we can have is we can have two instances. One is we can have a opcode and a 8-bit data, or we can have a opcode and a 16-bit data. Now, for an example, MVI A,05. So here the operand is specified in the instruction itself. So what it will do, it will move 05 immediate data 05 to the register A. So MVI A,05 is capable of moving immediate data 05 to A. Right now, likewise, we have second example ADI 06. So what it will do, it will add immediate data, that is 06, to the content of the accumulator and store the result in the accumulator. Likewise, we have LXI H, 2500. Now load HL pair with 2500. So just see, so these are the examples of immediate addressing mode. So in immediate addressing mode, the operand are specified in the instruction itself. We can have two different instances. We can have opcode or 8-bit data. We can have opcode or 16-bit data. So MVI A,05H is an example of opcode and 8-bit data. Likewise, ADI is the example of opcode and 8-bit data. Likewise, LXI H2500 is example of opcode and 16-bit data. So this is the property of immediate addressing mode. Now let us move on to register addressing mode. Now in register addressing mode, the operands are specified in the general purpose register. So that implies that a register is specified in the instruction itself. So in register addressing mode, the operands are specified in the operands are present in the general purpose registers, and the registers are specified in the instruction. Now what we have is we have the format, so opcode, source register, and destination register. So we have come across this particular instance. So MOV A comma B. So it will move the content of the register B to A. Right, so it will move the content of register B to register A, that is the accumulator. Likewise, add B. It will add the content of the register B to the content of the accumulator and store the result in the accumulator. So these are the examples of register addressing mode. So in register addressing mode, the operand is specified in the register, and the register is specified in the instruction. Now, likewise, what we have is we have direct addressing mode. Now, in direct addressing mode, the address of the operand is provided in the instruction itself. Again, I'll repeat it. In case of direct addressing mode, the address of the operand is specified in the instruction itself. So, for an example, STA25008. So here, what we are doing is we are storing the content of the accumulator in the address that is 25008. So we are storing the content of the accumulator to the address location 25008, right? Now likewise we have IN028. So we are storing the content of the accumulator in the port number 02H, right? Okay. So we are sorry, we are reading the we are sorry IN028. So what we're doing is we're reading the content or from the input port 02H to the accumulator, right? So these are the examples of direct addressing mode. So in direct addressing mode, the address of the operand is directly specified in the instruction itself. Now, a very important thing that you need to notice. So whenever we are working with memory location, whenever we are working with memory location in case of direct addressing mode, we need require 3 bytes. Okay, so we require 3 bytes because we require a byte for opcode, we require a byte for lower order address, and we require a byte for higher order address. So because memory the size of the memory address is 16 bits, right? So whenever we are working with memory, we require 3 bytes, and whenever we are working with IO devices, we require 2 bytes because we have boot address. 1 byte port address, right? So this is very much important. So in case of direct addressing mode, the address of the operand is specified in the instruction itself. And whenever you're working with memory location, we will be requiring 3 bytes. And whenever you're working with IO devices, we will be requiring 2 bytes. Okay. Now the next addressing mode that we have is called as register indirect addressing mode. So in register indirect addressing mode, the address of the operand is present in the register pair, right? Again, I'll repeat it. In register indirect addressing mode, the address of the operand is specified in the register pair. So for example, STAEXB. So what it will do, it will store the content of the accumulator to the address held by BC pair. So this we have already come across. So STAEXB is an instruction that is capable of storing the content of the accumulator to the address held by the BC pair. So this is an example of register indirect addressing mode. So in register indirect addressing mode, again I'll repeat it, the address of the operator is specified in the register pairs. Now, likewise, what we have is we have the implicit addressing mode. Now, implicit addressing mode, so there are a certain set of instructions which operate on the content of the accumulator directly. And the instruction does not require specifying the operand. So again, I'll repeat it. There are a certain set of instructions that works on the accumulator directly, and these instructions do not require specifying the operand, right? So for an example, CMA, complement the content of the accumulator. RAR, rotate the content of the accumulator to right towards right by 1. RAL, rotate the content of the accumulator left by 1. So this set of instruction works on the content of the accumulator. So this is called as implicit addressing mode. So in today's class, what we learned about is we learned about the 8085 programming model. The 8085 programming model. So the components of the 8085 programming model. So it has 6 registers, 1 accumulator, 2 16-bit registers, 1 flag register. So we went through the diagrammatic representation of the programming model. Then we discussed what are the various registers that are there. We discussed the role of the accumulator, the flag register, and then we moved on to the program counter and the stack pointer. And then we moved on to 8085 addressing mode. We try to understand what is an addressing mode. So addressing mode is the way of specifying the operand in the instruction. And then we went through the various addressing mode like immediate addressing mode, register direct, register indirect, and implicit addressing mode. And we've been through the description of the individual addressing mode, and we try to understand it with the help of examples, right? So this brings us to the end of the today's class. Thank you very much.